big picture. All right, this is going to be a big picture video for the class. We're going to revisit this later on, but we want to talk about this. There's going to be terms you don't know, and that's okay. But we're going to talk about why chemical reactions and how chemical reactions happen. All right, so when we talk, first thing we talk about is a chemical reaction. All right, what is a chemical reaction? All right, that's the question. What is it? All right, it can be broken down into two things. Right, a rearrangement of atoms. Right, which the law of conservation of mass, that exists, right? Law of conservation of mass. So it's a rearrangement of atoms and a redistribution of electrons. Right? So you're breaking and making bonds, right? It's breaking and making bonds. Right? Rearranging atoms, rearranging the bonds. You can either break the bonds and make new ones, or make new ones and break ones. Right? But that's how it works. That's a chemical reaction. All right? And so the question then becomes, what controls a chemical reaction? So what is the control of a reaction? What controls this reaction? Right? There are two controls. All right? There's what we're going to learn about is the kinetic control. And there is the thermodynamic control. All right, make that red. The thermodynamic control. All right, so these two controls, all right, of a reaction give us information. Now, think of kinetic control is, all right, the biggest thing about kinetic control, which we haven't talked about yet, and we haven't talked about any of this yet now, is activation energy. And so it's very similar. Now, again, I'm going to use a lot of human behavior in this course. Human behavior, we make decisions, right? Chemical reactions do not make decisions, right? If you put salt in the water, it's going to dissolve to a certain point. You put a bottle of water in the refrigerator, it's going to cool down. It doesn't decide that. It's not like, ooh, you know what, we're going to keep our temperature warm. We're going to cover up. It does not make decisions, right? Humans make decisions. But I'll still use human behavior every now and then as an analogy. So, when you talk kinetic control, all right, sometimes we might want to work out more, or lose weight, or get stronger, or save money, something like that. But we have to get over the activation barrier, right, of getting up in the morning and going to the gym, or getting up in the morning and going for the run, or getting up or taking every paycheck and putting some money aside, whatever we have to do, right? We have these barriers that we don't want to, that push, we don't want to break, right? And the barrier for a lot of reactions is this activation energy that we'll talk about in a few chapters. Now, with kinetic control, there are two things that come out of kinetic control. There is the rate of the reaction, all right, and it's how fast it goes. How fast does this reaction go? And then the mechanism, right, which is how the reaction goes, right? How does that happen, right? How did you, just going back to cooking, because cooking's very analogous to reactions. How did you make your spaghetti sauce taste so good, or your chicken taste so good, or how whatever dish you're making? So, right, the how matters. Okay. Thermodynamic control, which we'll spend more time this chapter, or this semester, breaks down into two things. Room there. It asks us if the reaction is spontaneous, and how far to completion does it go? Right? So does this reaction happen or not without me making it happen? Right? Just like, will my kids clean up their toys unless I make it happen? Chances are no, right? So that's just the way it goes. So when it comes to thermodynamic control, right, spontaneous, does it happen? How far does it go to completion? Maybe my kids will clean up a little bit, but not all the way, right? So maybe some of the react, right? And again, this is kind of true. Think about your gas tank, right? If you're using a gas tank to fill a lawnmower, all right? If you dump all the gasoline out, right, we're not going to use that gas tank now for drinking water because not every molecule of gasoline got out of that gas can, right? Doesn't all go, right? In fact, you can smell it for a long time later. So, right, so even things that transferring, that's not a reaction. That's just a physical change, so to speak. Doesn't go to completion. All right, thermodynamic control. So this comes into what we'll learn is the second law of thermodynamics, which controls that. And so if we talk about thermodynamic control of a reaction, right, because there's really two controls. There's the kinetic control, which is like mom, let's say, or dad, doesn't matter, and then the thermodynamic control, which is dad or mom, the other parent. And you have two parents that you got to ask for something to happen, for you can go out that night or go to this thing or that thing, and they both have to say yes, and they don't talk to each other, right? Okay, so some of us were good at playing parents, maybe, or ask your mom, ask your dad, or what thing. Here, kinetic control, can I go? Yes. Thermodynamic control, can I go? No, you can't go. It's that, and they don't. Well, kinetic said I can. Doesn't matter. All right, so they're both, independent. Like, can you go or not? Now, when we go to thermodynamic control, right, there's something called, all right, what makes these things happen? All right, okay, there's two terms that we're going to get, a couple terms here, right? We can have the overall term is what we're going to call delta G for the system is negative. That means nothing to us right now, and that's fine. There's two things. Delta S can be positive, which means it's entropy driven. Delta H can be negative, which is enthalpy driven, which you know that one. Or, of course, or both. Both could be true. All right? So what is delta H? If you remember delta H is heat transfer at constant pressure. All right? So my question is, what makes delta H negative? All right, so what do I mean by delta H negative? All right, that's a great question. And so if we look at delta H, if I have H here, enthalpy, right, which is heat content, it's kind of like chemical potential energy. What makes, in the reaction, what makes, if I have, for example, let's say you use C3H8, propane, oxygen gas, carbon dioxide, and water. If we burn propane, energy comes out, right? And if you've seen this before, delta H is the difference between the energy out. In this case, delta H is negative, what is it, 2260 maybe? I forget what it is off the top of my head. All right, kilojoules per mole. I'll be looking that up. And so we need to know what, why does energy come out of there, right? So what makes delta H negative? It's a great question. All right, and I'm almost there. It is 2044. 2044. Got the right number. Sorry about that. All right, so now we got, all right, what makes delta H negative, and it turns out to be a more stable arrangement of electrons. Right? How they're put together, right? Think of it this way: deck of cards. You could build a house of cards, and they might stay there for a minute. But if you put all the cards, chances are the cards will fall over, right? But if you have the cards just stacked up in a pile on a table, a lot more stable. Right? Same amount of cards. Same thing here. All right. So electrons, can be moved to make things more stable. So a lot of things happen to make the substances more stable. All right, they don't spontaneously make substances less stable. All right, so if we talk about the redistribution of electrons, there's two ways to do this. There's acid-base reactions, where there is no electron transfer because our oxidation numbers do not change. And then there are, of course, redox reactions, where we have an obvious change in our oxidation number, right? Because they are electron transfer reactions. So acid bases, a lot of times we're going to look at it as proton transfer. H plus transfer, proton transfer. So those are the two lenses we're going to look at reactions, and they do this to become more stable. All right, so why does this happen? Now we're going to go back and define all these terms this semester. We're going to find delta G and delta S and kinetic control, which is pretty much going to be something called activation energy, EA. We're going to define all this stuff. All right, spontaneous, which is delta G, and how far, that's going to be a capital K. It's going to make sense when we get there. All right, so that's what's coming this semester. All right. So that's the big picture, and I think hopefully that's what we're going to. Like, we're going to learn a lot of little details, which are fine, right? But this is the big picture. What happens? Why does it happen? And because again, what's the goal? To understand the behavior of something, right? I like to predict behavior. So if I know I add substance A to substance B, what's going to happen? That's the goal. And so being able to predict behavior and knowing how things are built and what things can tolerate and what things can't tolerate, and if it's toxic or all that stuff is important in predictability, and that's what we're looking for.